A liquid crystal display is a flat panel display or other electronically modulated optical device that uses the light modulating properties of liquid crystals. Liquid crystals do not emit light directly, instead using a backlight or reflector to produce images in color or monochrome. LCDs are available to display arbitrary images, as in general purpose computer display, or fixed images with low information content, which can be displayed or hidden, such as preset words, digits, and 7-segment displays, as in a digital clock. They use the same basic technology except that arbitrary images are made up of a large number of small pixels, while other displays have larger elements. Liquid crystal displays are used in a wide range of applications, including LCD televisions, computer monitors, instrument panels, aircraft cockpit displays, and indoor and outdoor signage. Small LCD screens are common in portable consumer devices such as digital cameras, watches, calculators, and mobile telephones, including smartphones. LCD screens are also used on consumer electronics products such as DVD players, video game devices, and clocks. LCD screens have replaced heavy, bulky cathode ray tube displays in nearly all applications. LCD screens are available in a wider range of screen size than cathode ray tube and plasma displays, with LCD screens available in size ranging from tiny digital watches to very large television receivers. Since LCD screens do not use phosphors, they rarely suffer image burn-in when a static image is displayed on a screen for a long time. For example, the table frame for an airline flight schedule on a door sign. LCDs are, however, susceptible to image persistence. The LCD screen is more energy efficient and can be disposed of more safely than a cathode ray tube can. Its low electrical power consumption enables it to be used in battery-powered electronic equipment more efficiently than cathode ray tubes can be. By 2008, annual sales of television with LCD screens exceeded the sales of cathode ray tube units worldwide, and the cathode ray tube became obsolete for most purposes. General characteristics. Each pixel of an LCD typically consists of a layer of molecules aligned between two transparent electrodes and two polarizing filters, parallel and perpendicular, the axes of transmission of which are perpendicular to perpendicular to each other. Without the liquid crystal between the polarizing filters, light passing through the first filter will be blocked by the second polarizer. Before an electric field is applied, the orientation of the liquid crystal molecules is determined by the alignment of the surface of the electrodes. In a twisted pneumatic device, the surface alignment directions at the two electrodes are perpendicular to each other, and so the molecules surround themselves in a helical structure or twist. This induces the rotation of the polarization of the incident light, and the device appears gray. If the applied voltage is large enough, the liquid crystal molecules in the center of the layer are almost completely untwisted, and polarization of the incident light is not rotated as it passes through the liquid crystal layer. This light will then be mainly polarized perpendicular to the second filter and thus be blocked, and the pixel will appear black. By controlling the voltage applied across the liquid crystal layer in each pixel, light can be allowed to pass through a varying amount, thus constituting different levels of gray. Color LCD systems use the same technique, with color filters used to generate red, green, and blue pixels. The optical effect of twisted pneumatic device in the voltage on a stage is far less dependent on variation in the device thickness than that in the voltage off state. I repeat, the optical effect of twisted pneumatic device in the voltage on state is far less dependent on variations in the device thickness than that in the voltage off state. Because of this, twisted pneumatic displays with low information content and no backlighting are usually operated between cross polarizers such that they appear bright with no voltage. The eye is much more sensitive to variation in the dark state than the bright state. As much as 2010 era LCDs are used in television sets, monitors, and smartphones, they have high-resolution matrix arrays of pixels to display arbitrary images using backlighting with a dark background. When no image is displayed, different arrangements are used. For this purpose, twisted pneumatic LCDs are operated between parallel polarizers, whereas IPS LCDs feature cross polarizers. In many applications, IPS LCDs have replaced twisted pneumatic LCDs, in particular in smartphones such as iPhones. Both the liquid crystal material and the alignment layer material contain ionic compounds. If an electric field of one particular polarity is applied for a long period of time, this ionic material is attracted to the surfaces and degrades the device performance. This is avoided either by applying an alternating current or by reversing the polarity of the electric field as the device is addressed. The response of the liquid crystal layer is identical regardless of the polarity of the applied field. Displays for a small number of individual digits or fixed symbols, as in digital watches or pocket calculators, can be implemented with independent electrodes for each segment. In contrast, full alphanumeric or variable graphics displays are usually implemented with pixels arranged as a matrix consisting of electrically connected rows on one side of the LC layer and columns on the other side, which makes it possible to address each pixel at the intersections. The general method of matrix addressing consists of sequential addressing one side of the matrix, for example by selecting the rows one by one and applying the picture information on the other side of the columns row by row. For details on the various matrix addressing scheme, let's see passive matrix and active matrix address LCDs. Illumination. Since LCD panels produce no light of their own, they require external light to produce visible image. In a transmissive tile LCD, this light is provided at the back of the glass stack that is called a backlight. While passive matrix displays are usually not backlit, like calculators, wristwatches, active matrix displays almost always are. Over the last years, the LCD backlight technologies have strongly been immersed by lighting companies such as Philips, Lumileds, and more. The common implementations of LCD backlight technology are CCFL. The LCD panel is lit either by two cold cathode fluorescent lamps placed at opposite edges of the display or an array of parallel cold cathode fluorescent lamps behind larger displays. A diffuser then spreads the light out evenly across the whole display. For many years, this technology had been used almost exclusively. Unlike white LEDs, most cold cathode fluorescent lamps have an even wide spectral output, resulting in better color gamut for the display, or even better color gamut for the display. However, cold cathode fluorescent lamps are less energy efficient than LED emitting diodes, and require a somewhat costly inverter to convert whatever DC voltage the device uses, usually 5 or 12 volts, to more or less 1000 volts needed to light the cold cathode fluorescent lamp. The thickness of the inverter transformers also limits how thin the display can be made. ELW LED. The LCD panel is lit by a row of white LEDs placed at one or more edges of the screen. A light diffuser is then used to spread the light evenly across the whole display. As of 2012, the design is the most popular one in desktop computer monitors. It allows to the dimness displays. Some LCD monitors using this technology have a feature called dynamic contrast, invented by Philips researchers Douglas Stanton, Martin Strumer, and Adriano Divan. Using pulse width modulation, a technology where the intensity of the LEDs are kept constant, but the brightness adjustment is achieved by varying a time interval of flashing this contrast light intensity light sources. The backlight is dimmed to the brightest color that appear on the screen while simultaneously boosting the LCD contrast to the maximum achievable levels, allowing the 1000:1 contrast ratio of the LCD panel to be scaled to different light intensities, resulting in 30,000:1 contrast ratios seen in advertising of some of these monitors. Since computer screen images usually have full white somewhere in the image, the backlight will usually be at full intensity, making this feature merely a marketing gimmick for computer monitors. However, for TV screens, it drastically increases the perceived contrast ratio and dynamic range, improves the viewing angle dependency, and drastically reducing the power consumption on conventional LCD televisions. W-LED array. The LCD panel is lit by the full array of white LEDs placed behind the diffuser behind the panel. LCDs that use this implementation will usually have the ability to dim the LEDs in the dark areas of the image being displayed, effectively increasing the contrast ratio of the display. As of 2012, the design gets most of its use from upscale larger screen LCD televisions. Red, green, blue LED array. Similar to the W-LED array, except the panel is lit by a full array of red, green, and blue LEDs. White displays lit with white LEDs usually have a poorer color gamut than cold cathode fluorescent lamp lit displays. Panels lit with red, green, blue LEDs have very wide color gamut. This implementation is more popular on professional graphics editing LCDs. As of 2012, LCDs in this category usually cost more than $1,000. As of 2016, the cost of the category has drastically reduced on some LCD televisions on same prices levels as the former 12 inches cathode ratio based categories. Today, most LCD screens are being designed with LED backlight instead of the traditional cathode cold fluorescent lamp backlights. While the backlight is dynamically controlled with the video information, dynamic backlight control. The combination with dynamic backlight control invented by Philips researchers Douglas Stanton, Martin Strumer, and Adriano Divan simultaneously increases the dynamic range of the display system, also marketed as HDR, high dynamic range television. The LCD backlight systems are made highly efficient by applying optical films such as prismatic structure to gain the lighting to the desired viewing directions, and reflective polarizing films that recycle the polarized light that was formerly absorbed by the first polarizer of the LCD, invented by Philips researchers Adriano Divan and Paulus Scariman. generally achieved using so-called DBF films manufactured and supplied by 3M. This polarizer consists of a large stack of uniaxial-oriented bifringed films that reflect the form and absorb polarization mode of the light. Such reflective polarizers using uniaxial-oriented polymetal and liquid crystals are invented in 1989 by Philips researchers Del Bru, Adriano Divan, and George Bambrin. The combination of short reflective polarizers and LED dynamic and backlight control made today's LCD televisions far more efficient than the cathode ray tube-based sets, leading to a worldwide energy saving at 600 watts per hour, equal to the 10% of the electricity consumption of all households worldwide, or equal to 2 times the energy production of a solar cell in a word. Due to LCD layer that generates the desired high-resolution images at flashing video speed using very low power electronics in combination with these excellent LED-based backlight technologies, LCD technology has become the dominant display technology for products such as television, desktop monitors, notebooks, tablets, smartphones, and mobile phones. Although competing OLED technology is pushed to the market, such OLED display does not feature the HDR capabilities like LCDs in combination with two-dimensional LED backlight technologies have, reason why the annual market of such LCD-based products is still growing faster, in volume, than OLED-based products, while the efficiency of LCDs and products like portable computers, mobile phones, and televisions may even be further improved by preventing the light of being absorbed in the color filters of the LCD. Although until today such reflective color filter solutions are not yet implemented by the LCD industry and did not make it further than laboratory prototypes. Such reflective color filter solutions still likely will be implemented by LCD industry or increase the performance gap with OLED technologies. Connection to other circuits. A standard television receiver screen and LCD panel today in 2017 has over 6 million pixels, and they are all individually powered by a wire network embedded in the screen. Defined wires or pathways firmly agree with vertical wires across the whole screen on one side of the screen and horizontal wires across the whole screen on the other side of the screen. To this grade, each pixel has a positive connection on one side and a negative connection on the other side. So the total amount of wires needed is 3 times 1920 going vertical and 1080 going horizontally, for a total of 6840 wires horizontally and vertically. That's 3 for red, green, and blue, and 1920 columns of pixels for each color, for a total of 5,760 wires going vertically and 1000 weighted rows for wires going horizontally. For a panel that is 20.8 inches wide, that means a wide density of 200 wires per inch along the horizontal edge. The LCD panel is powered by LCD drivers that are carefully matched up with the edge of LCD panel at the factory level. These same principles apply also for smartphone screens that are so much smaller than TV screens. LCD panels typically use thinly coated metallic conducting pathways on a glass substrate to form the cell circuitry to operate the panel. It is usually not possible to use soldering techniques to directly connect the panel to a separate copper-edged circuit board. Instead, interfacing is accomplished using either adhesive plastic ribbon with conductor traces glued to the edge of the LCD panel, or with an elastomeric connector, with an elastomeric connector, which is a strip of rubber or silicone with alternating layers of conductive and insulating pathways pressed between contact pads on an LCD and mating compact pads on a circuit board. Monochrome and later color passive matrix LCDs were standard in most early laptops, although a few used plasma displays. And the original Nintendo Game Boy until the mid-1990s were colored when color active matrices became standard on the old laptops. The commercially unsuccessful Macintosh Portable, released in 1989, was one of the first to use an active matrix display. Passive matrix LCDs are still used in the 2000s for applications less demanding than laptop computers and TVs, such as inexpensive calculators. In particular, these are used on portable devices where less information content needs to be displayed, lowest power consumption, and low costs are desired, or readability in direct sunlight is needed. Displays having a passive matrix structure are employing super twisted pneumatic, invented by Braun Boveri Research Center, Baden, Switzerland, in 1983. Scientific details were published. In double-layer super twisted pneumatic technology, the latter of which addresses a color shifting problem with the former, and color twisted to super twisted pneumatic is in which color is added by using internal filter. Super twisted pneumatic LCDs have been optimized for passive matrix addressing. They exhibit a sharper threshold of the constant versus voltage characteristic than the digital twisted pneumatic LCDs. This is important because pixels are subjected to partial voltages even when not selected. Crosstalk between activated and non-activated pixels has to be handled properly by keeping the revolution per second voltage of non-activated pixels below the threshold voltage, while activated pixels associated to voltage-disabled thresholds. Driving such STM displays, according to the alt and Pleshko drive scheme, require very high line addressing voltages. Velsen and Devan invented an alternative drive scheme, requiring much lower voltages, such that the STM displays could be driven using low voltage complementary metal oxide semiconductor technologies. STM LCDs have to be continually refreshed by alternating pulse voltages on one polarity during one frame and pulses opposite polarity during the next frame. Individual pixels are addressed by the corresponding row of column circuits. This style of display is called passive matrix addressed because the pixel must retain its state between refreshes without the benefit of a steady electrical charge. As the number of pixels and correspondingly columns and rows increase, this style type of display becomes less visible. Slow response times and poor contrast are typical of passive matrix address LCDs with too many pixels and driven according to the alt and Pleshko drive scheme. Wilson and Devan also invented a non-RMS drive scheme enabling to drive STM displays with video rates and enabling to show smooth moving video images on an STM display. Citizen, amongst others, licensed these patents and successfully introduced several STM-based LCD pocket television on the market. Bistable LCD do not require continuous refreshing. Rewriting is only required for picture information changes. In 1984, H.A. Van Sprang and A.J.S.M. Devan invented an STM-type display that could be operated in a bistable mode, enabling extreme high-resolution image up to 4,000 lines or more using only low voltages. Since a pixel, however, may be either in an on state or in an off state at the moment new information needs to be written to that particular pixel, the addressing method of these bistable displays is rather complex, reason why this display did not made to the market. That changed when, in the 2010, zero-power bistable LCDs became available. Potentially, passive matrix addressing can be used with devices if the right erase characteristics are suitable. which was the case for ebooks showing still pictures only. After the page is written to the display may be cut from the power while that information remains readable. This has the advantage that such ebooks may be operated a long time on just a small battery only. High-resolution color displays, such as modern LCD computer monitors and televisions, use an active matrix structure. A matrix, then film transistor, is added to the electrodes in contact with the LC layer. Each pixel has its own dedicated transistor, allowing each column line to access one pixel. When a row line is selected, all the column lines are connected to a row of pixels, and voltages corresponding to the picture information are driven onto all of the column lines. The row line is then deactivated and the next row line is selected. All of the row lines are selected in sequence during the refresh operation. Active matrix address displays look brighter than sharpened than passive matrix address displays of the same size, and generally have quicker response time, producing better images. This is gonna be the first part of the LCD resolution tutorial. See you next time. Have a nice day, and the next time I'm gonna provide you the second part of this tutorial. Thank you very much.